Hello students, welcome to the first lecture on the lecture series of relationship between numbers. Okay, so in this lecture, what we will do is we'll do a foundation work on the relationship between numbers topic. Okay, so what we'll be studying in this lecture is the concepts that are involved in relationship between numbers. Okay, so the concepts and types of problems on relationship between numbers. That is what we will be studying in this lecture. So let's start. So numbers are everywhere. Okay, we knew from the topic integers and whole numbers that numbers play a crucial role in quantifying objects. Okay, wherever we need amount or to quantify something, we need numbers. Okay, there are different types of numbers. We already learned natural number, whole number, and integers. Okay, we have already learned all these things. Okay, what these are. So numbers are everywhere, and this is how it is important. They help us to count our toys, share our candies, and know how many days are left until our birthday. Okay, you can say that my birthday is only 13 days to go, 12 days to go. Okay, these kind of statements are only possible when we have numbers to quantify things, to quantify days, to quantify years. Okay, how old are you? You're 13 years old, 12 years old. How can you say that? Because you have numbers. Okay, you can quantify. So the relationship between numbers allows us to tackle problems involving divisibility. Let's say, can we say that 6 is divisible by 12? 6 divides 12. Can we say this? Okay, that is when numbers, relationship between numbers come into picture. Okay, factorization, multiples, prime numbers. Okay, these are very important topics. Identifying patterns. In order to find patterns, what you need is numbers and relationship between them. Okay, so let's see what kind of concepts are involved in relationship between numbers. Okay, so the first concept is prime numbers. What are prime numbers? How they are important? Okay, actually in mathematics, prime numbers are the building blocks. Okay, in numbers, prime numbers are building blocks. Okay, if you study higher mathematics number theory, you will learn more about these prime numbers, why they are very very crucial, and they are everywhere in mathematics. Okay, so what are composite numbers? Okay, this is another concept. And what are factors, multiples, least common multiple? Okay, what is highest common factor? Okay, sequences and patterns, divisibility rules. These all are important concepts. Okay, that we need to learn. So let's explore each topic in detail. Okay, so the first concept is prime numbers. What are they? So prime numbers are basically positive integers that have only two distinct positive divisors, that is 1 and the number itself. Okay, and itself. So if x is a prime number, then what its property is only 1 divides x. Okay, that is 1 divides x and x divides x. Okay, this is the only condition or only property that it needs to satisfy in order to be a prime number. Okay, and what we have here is 1 is not a prime number. Okay, so this is a fact. This one is actually a fact itself. Okay, and 2, 3, 5, 7, 11, 13, you can see here that 1 divides 2. Okay, and 2 divides 2, 1 divides 3, and 3 divides 3. Does 2 divide 3? No, right? Because it will leave a remainder of 1. Does 2 divide 5? No, it will leave a remainder of 1. Does 3 divide 5? No, it will leave a remainder of 2. So that is why only 1 divides 5 and 5 divides 5 itself. Okay, the only way you will get zero remainder is by dividing by 1 or by dividing itself. Okay, so the same property holds for all these things. That is why these are the next prime numbers. Okay, there are other prime numbers after this, that is 17 is there, 19 is there, 23 is there, 29 is there, okay, 31 is there. Okay, these kind of numbers, it will be infinite. Okay, so the prime number series is actually infinite and you can always find a prime number. Okay, so let's go forward. So what are composite numbers? Okay, the numbers that are not prime, okay, and are positive. Okay, the integers that are positive and have more than two positive divisors. Two positive divisor, and this is more than two. Okay, it must have more than two, because if it has only two or one divisor, if it is have only one divisor, then it is one. Okay, that is not prime and not composite also. Okay, and it is not prime because it have more than two positive divisors, because primes have prime imply more than, sorry, not more than, only two positive divisor, one and itself. So composite numbers are also not prime numbers. Okay, so the two properties of composite numbers are, it have two more than two positive divisors and are positive integers. Okay, negative integers can't be called as composite numbers. Okay, so in other words, what we can say is that they can be divided by at least one number other than 1 and themselves. So because only if it is only divided by 1 and themselves, then it will be prime number. But if there is at least one more that can divide this number with a remainder of 0, then we will call this as composite number. For example, let's say we go for 6. Okay, so let's go for 6. Okay, that is 6. So for 6, what we have is 1 divide 6, 2 divide 6, 3 divide 6, and 6 divide 6. So see here, 1 divide 6 and 6 divide 6, but there are 3 and 2 also, and these are more. Okay, so not only this but also these two divide 6. That is why 6 is composite number. Composite number. Okay, so the examples of composite numbers include 4, 6, 8, 9, 10, 12, and so on. Okay, so in terms of 4, you can see that 1, 2, and 4. Here 2 is the extra one. Okay, 1 divides 4 and 4 itself divides itself. Okay, but 2 is another number that divides 4. So that is why this is composite. Okay, this is also composite. We have already seen that. In this case, 4 also divides 8. That is why it is composite. Okay, 3 divides it. That is why it is composite. So if you pick any number that divides it, okay, that is by dividing it by that number, you get a remainder 0. That is not equal to that number and 1. Then it will be called as composite. For 10, it is 5. I know that 5 divides 10. Okay, 5 divides 10. That is why 10 is a composite number. Okay, so let's test for primes, a trial division. Okay, so how can we know that a number is prime or not prime? Let's say for example 71. How can I know that this is not prime or prime? Okay, because only one can be true, right? Either this is true or this is true. Okay, so let's see. So we have a test here. Okay, that is trial division. Test if n is divisible by any prime number less than square root of n. Okay, if we find square root of 71, okay, so this will be around 8.2, or the smallest square root, or the smallest square root of 71 will be around 82, 8.2. Okay, because 64 square root is 8. Okay, and then the next square root is 81. Okay, and 81's square root is equal to 9. So this is in between them, so it is will be equal to 8.2 or 8.3, okay, or 8.3. So what we do is we test by all the prime numbers that are less than 8. Okay, so 1 is less than 8, 1 is not a prime number, 2 is less than 8, 3 is less than 8, 5 is less than 8, okay, and 7 is less than 8. So what we see is we try to divide 71 by 2. What we are left with is remainder 1. Okay. In this case, if we divide it by 3, then what we are left with is a remainder of 2. Okay. So also 3 doesn't divide. So 2 does not divide 71. 3 does not divide 71. And then what we see is by dividing it by 5, it leaves a remainder of 1. So that is why 5 does not divide 71. Okay. So what we see is we try to divide 71 by 7. Okay. So does 71 divides, okay. What we can see here is it leaves a remainder of 1 because 7 into 10 is equal to 70 and will be left with a remainder of 1. So also 7 does not divide 71. So since all these are leaving some remainder that is not equal to 0. Okay. So what we can say is that if n is divisible by any such prime, then n is composite. Since it is not divided by any of these primes, what we can say is that it is prime. Okay. Let's say another example. Let's see. Okay. Let's see the number 27. Okay. So what is the least square root complete square before 27? So that is 25, right? 25. Because 25 square root is equal to 5. Okay, the least number that is a complete square is 25. Okay, so 5. So all the prime numbers less than equal to 5 are 1, 2, 3 and 5 itself. So this is not a prime number. If we divide 27 by 2, then what we are left with is a remainder of 1. So 2 does not divide 27. And if we divide it by 3, the remainder is equal to 0. Okay. So in this case, what we can see is that 3 divides 27. Okay. So we got a number that actually divides 27. Okay. And we don't need to further test it as we have got the number. A number that leaves a remainder 0 and is less than the least number that is a complete square. Okay. So before 5, what we have was 2 and 3 as prime numbers. And actually 3 divides 27 and leaves a remainder of 0. So what we can say here is that this point comes into picture and n is a composite number. So 27 is composite number. Okay. So another test is called the Fermat's little theorem. Okay. Pick a random number such that 1 is less than a is less than n. Okay. Then what we do is compute a power n minus 1 modulo n. Okay. If the result is not 1, then n is not prime. Okay. We'll see an example on this. So the third concept is factors and multiples. Okay. So factors and multiples, what it tells us is factors of numbers are the positive integers that divide the number without leaving any remainder. So if we, for example, we see the factors of 12. Okay, 1 leaves 0 as remainder, 2 leaves 0 as remainder as it is even, and 3 into 4 is equal to 12. That is why 3 and 4 both leave a remainder 0. 6 into 2 is equal to 12. That's why 6 also leaves a remainder of 0. And 12 divides itself, so it also leaves a remainder of 0. So we can see that this is the multiple series or series of multiple of, not multiple, factors of 12. Okay, so this is a series of factors of 12. Okay, so on the other hand, multiples of a number are obtained by multiplying the number by positive integer. So if we try to see multiple series of multiples of 4 is equal to 4, 8, 12, 16, okay, 20, 24, and so on. Okay. So let's see another important concept, that is LCM, that is least common multiple. Okay. So what we need to see in this is, since these terms are included in the naming scheme, so multiple, you know that first what you need to see is, if you want to get the least common multiple of two numbers, okay, it is always valid when it is asked about two numbers. Okay, LCM can't be find of a single number. So if you are trying to find LCM, then you need at least two numbers. Okay, so LCM is what? LCM is the smallest positive integer that is divisible by 2 or more given numbers, okay, without leaving any remainder. Okay, so what we need to do first is, we need to find the multiple series. So let's see, I need to find LCM of 2, 3, and 7. Okay, so first what you need to do is, you need to find the series of multiples of 2, 3, and 7 individually. So series of multiples of 2, 3, and 7 individually will be 2, 4, 6, 8, 10, 12, 14, so on. Okay, for 3, for 2 this is, okay, for 3, 3, 6, 9, 12, 15, 18, and so on. Okay, so for 7, what we have is 7, 14, 21, 28, okay, then 35, and so on. Okay, now since we have got the multiple series, our series of multiples, then what we need to further exhibit is, we need to find the commons between these three series. Okay, let's start from here. So 2 is not common, 4 is not common, 6 is not common, 8 is not common, 10 is not common, 12 is not common, although 12 is common in these two but not common in all the three. Okay, and 14 is not common, so we need to evaluate it further. So what it will be is equal to 14, then it needs to go to 42 actually. Okay, for 40, up to 40, 42, 44, and something like that, and then it is 21, 24, 27, 30, 33, 36, 39, 42, and so on. Okay, and this will be equal to 42, 49, okay, 56, and so on. So 42 will be the least among these. Okay, the least common multiple. Okay, so the answer will be equal to 42. Okay, we will also learn another property, that if we are trying to find LCM of prime numbers, then the LCM is their product. Okay, so 2 into 3 into 7 is equal to 42. So we'll learn this property in the upcoming slides. Okay, so LCM of AB is equal to C possible only when C divides A and C divides B belongs to the integers. Okay, so if a number is LCM of other two numbers, then it is only possible when C divides A and C divides B. Okay, that must be a non-zero quantity. Okay, non-zero and non-decimal, that is a complete integer. Okay, so let's learn what is HCF. Okay, so HCF is nothing but the highest positive integer that divides two or more given numbers without leaving any remainder. So HCF is highest common factor. Okay, so what we need to do is, if we are asked to evaluate, let's say, HCF of A and B, okay, what we will do? Okay, we always try to go from the right to left. Okay, first we need to find the series of factors, or the factors of A individually. Okay, let's say for A it is x1, x2, x3, x4, and so on. Okay, and let's say for B it is y1, y2, y3, y4, y5. Okay, and let's say x2, this is in ascending order. This is also in ascending order. Okay, so basically x2 is less than x3 is less than x4, and y1 is less than y2 is less than y3 is less than y4 is less than y5. And let's say x2 is equal to actually y3. Okay, and x2 x1 is equal to y1. Okay, let's say for example, then what is the HCF of A and B is x2 or y3. Okay, because both are same. Let's see this thing in an example. Okay, so let's say you want to find the HCF of 12 and 15. Okay, highest common factor. So you need to find the factors of 12, that is 1, 2, 3, 4, 6, 12 itself. And for 15, what it will be is 1, 2, not 2, 1, 3, 5, okay, 15 itself. Okay, so what you can see is the factors of 12 and 15 individually. So the next thing is find the common between them. So what are common between these two? So 3 is common between these two. Okay, is there anything else? 1 is common between these two. Okay, so what is the highest among these? So between 1 and 3, highest is 3. So HCF of 12 and 15 is equal to 3. Okay, so this is how we evaluate HCF. So there are some important formulas. Okay, if A into B, then this is actually equal to LCM of AB into HCF of AB. Okay, we can take an example to learn this in a better way. So let's say A is equal to 5, B is equal to 6, let's say. So 5 into 6 is equal to 30, you know, right? And LCM of 5 and 6 into HCF of 5 and 6. Okay, so LCM of 5, 6 is equal to actually, what we need to do is find the multiples of 5 and 6. So it will be equal to 30. Yeah, this will be equal to 30. We can find it 5, 10, 15, 20, 25, 30. Okay, and for 6, what we can do is 6, 12, 18, 24, 30. So the least is 30, you can see here. Okay, that is why LCM of 5, 6 is 30 into HCF of 5, 6. So highest common factor for 5, what are the factors? This is prime number, so 1 and 5 are the only factors. And for 6, 1, 3, 2, 6, these are the factors. So the only common is this one, and the highest common factor is actually 1. Okay, so this is 1, that is equal to 30. Hence, this can be verified by this observation. Okay, so this is the first observation, and this is the second observation. So LCM of ABC is equal to AB into C into HCF of ABC whole by HCF of AB into HCF of BC into HCF of AC. Okay, we will see an example of this when we do the exercises. Okay, and the third part tells us that HCF of ABC is equal to A into B into C into LCM of ABC whole by LCM of AB, LCM of BC, LCM of AC. So you can actually remember these two by comparing. Okay, first case, what you did was you found LCM of 3 different numbers, right? So when you try to find the LCM of three numbers, that is A, B, C, what you do is you use HCF in the formula. So ABC is multiplied in the numerator, and with that we multiply the HCF of A, B and C. Okay, you want to find the LCM of ABC, and what you do is you give ABC to the numerator and multiply it with HCF of ABC. And what you do in the denominator is you find out the HCF of any two. Okay, so that all the three possibilities are covered and multiply them together. That is, you try to find HCF of AB, then you try to find HCF of BC and HCF of AC and multiply them. Okay, multiply them. Then you find the LCM of ABC. And if you just swap the positions there, okay, swap HCF with LCM, that is, you try to find HCF of A, B and C. Then what you do is you give ABC to the numerator and multiply with the LCM of ABC. Okay, and what you do in the denominator is you find LCM of all the two combinations possible out of those three and multiply them together in the denominator. So LCM of AB is multiplied with LCM of BC is multiplied with LCM SC. So you can easily remember these two by comparing. Okay, because only thing happened here is LCM and HCF positions were swapped. Okay, so some important formulas are A by B, C by D, E by F. So HCF of all these three is equal to actually HCF of A, C, E. In the numerator, what we get is we get A, C, E, HCF, and in the denominator, what we give is LCM of B, D, F. Okay, the denominators here. Okay, you need to learn these formulas and practice them well. And LCM of A by B, C by D and E by F is equal to LCM of ACE whole by HCF of BDE. So also you can see here is that the roles are just swapped. Okay, all the things are remain same. Okay, so you can also remember these two by comparing. All you need to do is practice one and you will get the other one, because what happened was only LCM and HCF were swapped. Let's see the fifth concept, that is sequences and patterns. Okay, so what is a sequence? When we talk about a sequence, we are talking about a set of things that come one after another in a specific order. Okay, for example, morning, you might have a sequence or activities. Okay, first you wake up. Let's see the morning sequence. First, what you do is you wake up, then you brush your teeth. This is one. This is two. The second thing you do in the sequence, and after that you get dressed. Okay, this is three. Third part in the sequence, and finally you eat breakfast. Okay, this is something that we repeat every day. Okay, the order is same. You don't brush your teeth first and then you wake up. Okay, you first wake up, then you brush your teeth, and then you get dressed, and then you finally eat your breakfast. You never do like eat breakfast one day first, then you wake up, or in the next day what you do is you eat breakfast first, then you brush, then you wake up. This doesn't happen, right? So the sequence is this: you wake up, then you brush your teeth, and after that you get dressed, and finally you eat breakfast. So sequence is basically a pattern. Okay, so each activity happens in a particular order. Okay, order is very important here. So, and that order makes up a sequence. So basically that order is a sequence. Here the order of first waking up, then brushing your teeth, and then getting dressed, and finally eating your breakfast. That is the order here in the sequence. Okay, this order is a sequence here. So what is a pattern? A pattern is something that repeats over and over in a regular way. Okay, you must be thinking about a sequence and a pattern. What's the difference? Okay, so let's say you have a sequence 1, 2, 3, then 1, 2, 3, 1, 2, 3, and so on. Okay, so you can see here this is a sequence. Okay, but the sequence is only 1, 2, 3 because after that the pattern repeats itself. So 1, 2, 3 is a pattern. But if you see 1, 2, 3, 4, 5, 6, and so on, this is a sequence, but it's never repeating, right? So that is why all the sequences can't be pattern, but all the patterns are sequences. Okay, patterns are basically sequences where stuffs are actually repeated over and over again, okay, in a regular way. Let's get to the next. So patterns can be find out in many places. You might see them in geometrical objects. In nature, you can find out that the number of petals in a flower are actually pattern. Like if you see 5 petals in a rose, you will see most of the rose that are bloomed in that tree have 5 petals. Okay, that pattern continues. Okay, so in nature, in rainbow, you can see always see that curve, right? You never see a straight rainbow, you always see a curved rainbow, right? So the designs on your clothes or even rhythms of songs. Okay, let's end the lecture here. Thank you.